Hello? Oh, it's not this. Hello? Okay. Yeah. So we have everyone here. Oh, Riley's Riley stopped attending. Hopefully he looks at the lectures. Okay. There was a homework due today. And I'll post the new homework. I was deciding what topic to start. I was a little debating. So hopefully in the next couple of hours. So homework 8 will be due on Wednesday, October 7th. And I did announce, did I say about the class? So there'll be no class. October 5. Which is Monday. Did I say that, Tom?
Mm-hmm.
Okay. So, and midterm 2. Friday. I did not hear anything from you guys, so I assume in class is fine. So we're gonna. I think the case. Did you guys check the cases today? Today something is supposed to come on, right? Can you quickly check?
I did check, the website was down.
Oh. Okay, I think it is going good as far as I know. So we have it in class, and hopefully everything works out well. Okay. So that's midterm 2, and yeah. Any questions in general? We talked about multiple expansion. And today, I want to see the connection between multiple expansion and let's say Legendre polynomials. All of you guys have taken math methods in one form or the other. It's called theoretical methods when we take the first 301 course. Have all of you guys taken it? I remember a few of you. Matt, did you take math methods with me or?
Yeah, I took it with you.
Oh, you took it with me. Okay, sorry. Yeah, that's right. I don't remember. Yeah. Okay, so that means all of you guys have seen or at least heard about Legendre polynomials. So let's see the connection between the two. So remember what we did is R minus R prime. As I said, if you want, you can put a Q also in it, and there is a 1 over 4 pi epsilon. So that's the main point there. So this is equal to 1 over R. If there was a Q, it is the electric potential due to a charge at the origin. Then we have R dotted with R prime over R cube. And the next one was, we wrote it in the following form, right? So this is R dotted with, yeah, let me write it in the following form. So this is 3 by 2. What is it? This R prime minus 1 R prime square dotted with R over R raised to 5. Now the claim is there are higher terms. And clearly, we said this is the monopole term. This is the dipole term, the quadrupole term. And the next one, so let's put it in the right place. So let's say this is L equal to 0, right? We'll call this L equal to 0. And this is L equal to 1. This will be L equal to 2. And this will be, next one will be L equal to 3 and so on. Actually, in that sense, maybe I said it wrong before, right? I said this was next order was octuple, so let's start octuple like it. This will be what? I think the way to say this is so dipole is 2 times. Yes, so it is 2 times 1 pole. Right. So this is 2 times 2 pole. In general, this next one will be 2 times 3 pole. And in general, there will be 2 times L pole. 2 times L or 2 L pole. So how many poles was this? Yeah, 2 into 6, right? So I said a couple. So 6 will be what's it? Hexapole and so on. So in general, there are 2 L poles if you want. So one would like to see is there a general construction we can make? Obviously, using this vector feature, it is not convenient. Very quickly, we get into 3-dimensional, 4-dimensional quantities, and that's where the Legendre polynomial sort of comes in handy. But remember, Legendre polynomials was not constructed to deal with electrostatics, but the idea is the same. This potential is exactly the same as gravitational potential, so it's built in there and comes out useful. So all these dipoles, quadrupoles are same ideas as there in gravity also. Pretty much exactly the same. So for that purpose, so let's start over again with this left hand side, and let's do the following. So this is 1 over r minus r prime magnitude, and this is equal to can be written as a square, right? So this is 1 over r minus r prime dotted with r minus r prime, and then you take a square root of that, right? That's a way of writing the magnitude. And that's the same as we saw this when we were doing that electric potential due to a charged sphere. This is r square plus r prime square and minus 2 times r dotted with r prime, right? And this is 2 times r dotted with r prime. And r dotted with r prime, we said, is actually 1 over minus 2 r prime, and r dotted with r prime has this nice feature that is the angle between the two vectors, right? So this is cosine of gamma. Okay, this is a place where both gamma and r show up together, and my r's look like gamma. So this is gamma. Is this better? Does this look like gamma at all? Is this okay? Yeah, that's gamma and then the square root again. Okay. So in general, our diagram is so if I had my z-axis here, my z-axis in general, that's my r, and this could be your r prime. Then that's z hat, let's say. Then we know that this makes an angle theta, and this makes an angle theta prime. These two need not be in the plane, right? In general, these two need not be in the plane. So this can make another angle phi here, and this could make another angle phi prime here, which is how much out of the plane. Is that clear what I mean? Keep the theta fixed and bring it out of the plane. That decides how much phi angle it is. Is that clear what I mean there? Well, no. So let me elaborate on that maybe. So think of this as your axis, and that's your cone. That could be one. And that could be another cone up there. That's your, and this could be down here. Notice that this vector is not in the same plane, it is coming out of the plane, and how much angle that makes is decided by phi prime. Is that clear? Any questions there? Is this visible? Yeah. Okay. So so what is cosine gamma in general in terms of theta and theta prime? We did this last time. We said cosine of gamma is equal, gamma is cosine of theta 1 or theta, cosine of theta prime times plus sine of theta times sine of theta prime times cosine of phi minus phi prime. Remember that? Right? The dot product of these two vectors, if you were to write it in terms of theta and theta prime, you will have cosine theta prime, sine theta prime, and cosine of phi minus phi prime. Since like I did do this in the class of, I think it was 2 weeks before, I will encourage you guys to do this as an extra credit. Just rederive it. I mean, we did this in one of the lectures. It's just 2 steps. Don't spend too much time on this.
We just derive it.
Yes, derive that. This is what you do is write R is equal to sine theta cosine phi in the I direction plus sine theta sine phi in the j direction plus cosine theta in the k direction, and there is an r prime also there, right? And find r dotted with r prime. That will give you the right hand side. And equate it with the angle between them. So this is the angle between them, that's gamma. So on the left hand side you have r prime cosine gamma, and on the right hand side you will get this will be your answer. Is that question clear? Is that clear? Yeah. Okay. Let's do one simple thing. It doesn't actually matter, but let's choose. So let's choose R to be along the z-axis. That means to say that theta is equal to 0, which implies that cosine of gamma is actually equal to cosine of theta prime. When you choose this R to be along this direction, this theta prime becomes theta prime becomes equal to gamma. That's just an unnecessary simplification at this stage, but let's do that. So my 1 over r minus r prime becomes equal to 1 over r square plus r prime square minus 2 r prime cosine theta. Tell it again. Oh, theta prime. Yes, thank you. Pull this out. So I have 1 over r, and let me write this as 1 plus r prime over r square minus 2 r prime over r cosine theta prime. So I have this quantity as 1 over r times, let me write this as 1 over 1 plus x squared minus 2x cosine theta prime. Just a small tiny notation at this point, so that x is, so here x is equal to r prime over r. So if I expand this out as a Taylor expansion, the expectation is that I should get this structure in there, right? So this was basically a Taylor expansion of this expression. So if I were to do a Taylor expansion of this, I should get pretty much the same expression in there, and that's what we will define. So let me define the things here. So this is going to be 1 over r, and I want to expand this out. I'll tell you, we'll actually explicitly expand that, but let's expand. Let's say that this is x raised to L, and L equal to 0 to infinity. So I want an expansion of this form, and if that is the case, then I should have coefficients in there, and these coefficients will be called the Legendre polynomials, EL cosine theta. So this will be called Legendre polynomials of order L. What is a polynomial? What's the difference between a polynomial and a function? A function is a series when you take it all the way till infinity, like sine function. It doesn't end, right? If you were to write sine theta as an expansion in theta, it is theta, theta cube, theta raised to 5. It keeps going, it doesn't end. If it ends, it's called a polynomial. Right? So polynomial means there is a finite number of terms in this series. But we're not saying that this series is finite, we are saying this term comes out to be a polynomial. That means if you were to expand this out, there will be a finite number of terms. So I'm not saying that this is finite. It is this function as it's like a quadratic polynomial, cubic polynomial, quartic polynomial. So that's what we mean. So if you were to expand this as a function of theta, then it will be finite number of terms. That we'll see that. So the goal is simple. So expand this and capture the coefficients, right? At least first few terms, we should be able to do that quickly, and then we will write a general formula for that. So let me change the camera. So to identify, so again, 1 over, so this is our definition if you want, 1 plus x squared minus 2x. Oh, this is theta prime, by the way. So 2x. And at this stage, I'm just defining, so let me write cosine theta so that I don't have to rewrite theta prime all the time. But it'll come back, and but whenever we use it here, again, we have to put that x theta. So our definition is sum L equal to 0 to infinity x raised to L, and PL cosine. We pretty much did this in mathematics also, like the motivation or the theme was very slightly different. There was no dipole moments, that's all the differences. So let's Taylor expand this. What is the Taylor expansion of 1 over, or let's say 1 plus x raised to n? How do you Taylor expand this? What's the expansion? One plus n times x. Next one.
So this and x squared.
And the next one is n minus 1. And there's a 2 factor. And next one, the pattern is then the n into n minus 1 times n minus 2 over 3 factorial and x cubed and so on. If n is an integer, this will end, right? This will end because eventually it will hit n itself. So it will stop. So that's why it becomes a polynomial. But if it's not an integer, for example, 1 by 2, then it keeps going. Right? It will not end. Only if it's an integer. If n was an integer, then this will become 0 somewhere. We are interested in 1 plus x raised to 1 by 2. Not really x, it is x squared plus minus 2x. But let's see what is this. So this is 1 minus 1 by 2x plus, there is a minus 1 by 2, minus 1 by 2 minus 1 is minus 3 by 2, so it is plus 3 by 2, and that's 3 by 8, right? So it's 3 by 8 x squared. And this one is 1 by 2, 3 by 2, 5 by 2. That's 15 over 8. 15 over 8 divided by 6. So 3 cancels out. So it's 5 over 16. It's minus, next one will be minus. So minus 5 over 16 x cubed. That's your series. So let's substitute that in here. That's 1 minus 1 by 2 of x now is this whole thing, correct? So it is x squared minus 2x cosine theta. And the next term will be plus 3 over 8 x squared minus 2x cosine theta squared. And next one will be minus 5 over 16 x squared minus 2x cosine theta cube, and so on. Let's stop cube, right? So that is the power, dipole should come in as a power of square, or sorry, power of x, and then x squared should give you the quadruple. So we'll go to x cubed. So that's equal to, let's expand this out. So that's 1 minus 1 by 2 x squared plus x times cosine theta. This one is 3 by 8 plus 3 by 8 x raised to 4 minus 4x cubed cosine theta, and there will be plus 4x squared cosine squared theta. I think that's good. Yes, Christian.
Do we change it to cosine theta normal? Is that prime?
Oh yeah, let's make it prime if there's a confusion. Let's make it prime. Yeah, it's not very bad to keep following it because theta there I set it to 0. Right? It could be confusing. Let's keep theta prime. It's good to keep it as theta prime because theta prime is a source that we're talking about sources. But source and observer, eventually we will see that there's a lot of symmetry. Okay, the next is 5 by 16, so now I think I can even get rid of this. So I can keep going on this straight line maybe. So this is equal to minus 5 by 16. This is x raised to 6. I don't have to care for this x raised to 6 because I've dropped, right? So here there are powers of 6. Anything more than 4, I can drop because I'm not following it up again, right? I cannot do anything regarding 4 or 5 or 6 because I already dropped it. This is not relevant, but just keep it anyway. So minus square of this and 1 of this. So 3 into 2, so it's 6. I suppose, and catch me if I'm doing anything wrong, and then there's the sign of theta prime. Next one will be plus. This will come 2 times square of this, so 3 into 4, so that's 12, x raised to 4. Again, doesn't matter because all these are supposed to be dropped. Cosine theta prime square, cosine square theta prime. And the next one is the important one. So this is cube of this. This is minus of cube. So this is 8. 8x cube cosine cube theta prime. The higher terms have 4, 5, and 6 in it. So I don't even care for this. I cannot account for it unless I go further out in the series. So forget about the 4, 5, and 6 terms. They will work under Q. Now we just have to collect things together. So there's only one 0th order term. Linear term, this all starts from x squared, this starts from x cubed. So the linear term is only here. So that's plus x times cosine theta prime. What about x squared? Plus x squared. So taking care of this, x squared comes, again, it doesn't show up here. There's a term here and a here. 4 by 8 is 3 by 2. And we see our quadruple moment in here, right? At least that structure is in there. So quadruple. So this is our dipole cosine theta. If I mean, you're not seeing it. There's a dot product in there, right? So here is the dot product. So this 3 by 2, 1 by 2. So just oh, check. I'm having some connection issues, so I will watch the rest. Okay, this afternoon once it's okay. So I think Travis dropped out. Is it clear? Matt,
Yeah,
can you read? Yeah, it is clear, right? Yeah.
Yeah, it's good.
I haven't had any issues.
Okay, good. Yeah. Okay. Okay, and then there's an x cubed term. X cubed, we have everything. From this term onwards, it starts from x raised to 4. So we can capture all of x cubed. Right? We don't really have to worry about dropping the higher terms. So x cubed, we do have everything. So x squared, actually, I captured this. And x squared, where did this come from? Okay, x squared. X raised to 4, actually, I cannot keep. So I have to drop this. Right? X cubed. This is 5 by 2, right? Plus 5 by 2 cosine cube theta prime. So that's taken care of. And finally, this one, which is minus 3 by 2, comes with cosine theta prime. And so on. So we can now, if we were to connect with this, remember this is equal to 1 plus x how do you write this? So this is P0 cosine theta prime plus P1 cosine theta prime times x plus x squared times P2 cosine theta prime and so on. Right? So we can read this out now. What does your Legendre polynomial equal? So P0 cosine theta is equal to just cosine theta of theta prime, cosine theta prime. P1 of cosine theta prime is actually mistake, right? Right. P0 is this 0 power, right? So it's 1. P1 is cosine theta prime. P2 is equal to 3 by 2 cosine squared theta prime minus half, and P3 cosine theta prime is equal to 5 by 2. And so on, it keeps going. Notice that theta prime, what is the domain of theta prime?
0 to infinity.
0 to?
Infinity.
No, it's an angle, right? It's an angle. How far does it go?
2 pi, right?
Does it?
5. I thought 5 went 0 to
5 went to 0 to 2 pi, but pi,
5. Oh,
one of the, this is the spherical coordinate, right? So it goes only till pi, right? Think of.
confused. I learned it in math first.
Yeah. So this phi is the, let's say, phi is the latitude, right? Yeah, latitude. Is that clear on Earth?
Just because when I learned polar coordinates, it was always theta, so that was associated.
I know. So in this case, that confusion, yeah. I in the beginning warned that physics and math they swap, right? But this is latitude. This way it is clear, right? Phi is the latitude, and theta is the. Oh no, I said it wrong. This is the longitude, and this is the latitude. Right? But then theta goes from 0. Like, what is the latitude of Earth? Sorry, of our place, carbon, roughly?
Like 30 maybe?
Yeah, 30 to 40. It said out 39 actually, 40 degrees. Is that clear what I mean?
Yeah.
So this is sphere. So this is the angle, right? So this is Carbondale, right? So this is angle. So this is okay. So this is. I would like this is our angle theta. So how do you say this? Pi minus latitude, right? Pi by 2 minus latitude is equal to theta. Better? Add this angle to that to get the how do you say this? Yeah, pi by 2 minus theta is the latitude. Better? Yeah. So this is the latitude. And that's 40, approximately 39 degrees from us, I think. Let's say 40, I might be wrong, probably. And what is the longitude, by the way? Estimated, just guess, roughly. Where is phi equal to 0?
What's it called? The
Greenwich. Greenwich. Where is it?
The primary.
Yeah. Which city does it go?
Greenwich.
London, basically. Because in those days, London was big and almost more powerful, right? So they decided all these things. These days, it's decided here. So phi is equal to 0 there. So how much is Carbondale then, roughly? roughly.
Google says -90.
Oh, negative 90, I see.
Yeah, just about negative 89.2.
Yeah, cool.
Says
Yeah,
Google.
okay, yeah. Oh, so you just searched it. That's perfect. Yeah. So now you know precisely. 89 and is 39 correct?
37.
37. Okay, I'm wrong. Okay, 37. 37. Well, so 37 and this is phi is approximately 89 or something. Yeah. Cool. Right, so that's what it is. So, but point is, this goes from 0 to pi. Right, it just needs to go till here. And why doesn't it go all the way to 0 to pi? Because then it starts repeating, right? If you want to come here, you can get the same thing by going here and then rotating to this point. You start double counting if you actually go more than pi. Clear? Right, so that's theta prime goes from 0 to pi. That means cosine theta prime goes from where to where? And cosine of phi is -1. Oh, I don't want to put that this way. So -1 to 1. But this is corresponding to this, and that's corresponding to that. Cosine of theta prime goes from -1 to 1. So let's define x, which is not this x, not the, that is good to write. Like this is how you define your Legendre polynomials usually. P0 of x is equal to 1. P1 of x is equal to x itself. P2 of x is equal to 3 by 2 x squared minus 1 by 2, and P3 of x is 5 by 2 x cubed minus 3 by 2 x. Notice there is a finite limit on this x power, right? So that's why it's called polynomials. Like they don't go as an infinite series. In fact, in general, so one might be curious, what is this pattern? It's actually doesn't show up. This pattern is not very obvious here. It seems to suggest that this is 3 by 2, 1 by 2 is called fraction of tau. But the general formula for this is PL of x. It is d by dx. So it's take derivatives L number of times of what? It is x squared minus 1 raised to L and L factorial. This is called Rodriguez formula. I'm not. This is recently has been called Rodriguez formula. If you look at the literature more than 30 years back, it is not very popular, but it must be correct. Rodriguez formula. So usually in exams, I like to ask, like if I give you this and get the fourth, like we have done till 3, find the fourth one, right? P4 of x, right? Find the first, it's very simple exercise. Okay, so that's good. So now, notice that this was our quadrupole moment, right? Quadrupole moment sort of sat there. So it's good to see where does it sit in. So let's. So 1 over r minus r prime. Let's write it again. This was 1 over r, right? Q over r if you want, plus r dotted with r prime over r cube plus r dotted with 3 by 2 r prime minus 1. Actually, let me expand this. This is multiply the sufficient number, return the sufficient number of times. This can be written as 3 by 2 r dotted with r prime square minus 1 by 2 times r square times r prime square divided by R is 5. This seems to suggest that I can write this as, if I write this as dot products 1 over R plus R prime or prime cosine of theta prime, remember. Otherwise, it is cosine of gamma if you want. So since it is R dotted with R prime coming in, it is pretty much cosine of gamma divided by R cubed plus 3 by 2 R square R prime square cosine square theta prime minus 1 by 2 R square R prime square divided by R raised to 5. And we quickly see this, this is P0 cosine, or this is P0 cosine theta prime, this is P1 cosine theta prime, and this is actually P2 cosine theta prime. So if I can write one more line underneath, yes, I can. So this is equal to 1 over R plus one of the R cancels out. And so let me get this R completely out. So let's say 1 over R is completely outside. So this is 1 plus R prime over R times cosine theta, which is P1 cosine theta prime. If I take an R square common, cancel out the 1 over R cube there, one of the R has gone out. So this is plus R prime over R square, and whatever is left out is P2 cosine theta prime, and you see the pattern, right? So apparently this is equal to 1 over R. Our potential or multiple expansion is nothing but equal to 0 to infinity R prime over R raised to L times PL sine theta prime. So at least if you're on the axis, this is actually right if you're on the axis. Otherwise, this pulling out doesn't work normally. So we have to do a little more work for getting other features in there. But whenever you're on the axis, your dipole moment is exactly given by the Legendre polynomials if your observation point is on the axis. Otherwise, all these features doesn't come out very well. This is R dotted with R prime there, right? So in this sense, like if the observation point is on the z-axis, then multiple or you want a q times, so this, so let's say q, what should I call multifold? So maybe what is q? So monopole is q, right? So sum over q. Sum over q. Dipole is sum over QL times QL times RL. Right? Q1, R1, Q2, R2, and so on. Only when your let me just make this a single point chart. Right? A point chart. So this is Q. Dipole will be Q times R, right? R prime, and dipole. Oh, sorry, quadrupole. Will be Q times P2. So first of all, I have to make an R prime. How many powers? R prime raised to 2. Okay, this is R prime raised to 1. This is R prime raised to 2. And P2 cosine of theta prime. Next term, so the L pole, right? The dipole, the 2L pole. That's what we call it. So this will be Q times R prime. This is not L, this is R prime raised to L. This is PL cosine of theta prime. Quadrupole has L. Next one will be 3, and so on. That's clear.
The R prime's vectors here.
This is not a vector at this time. This is getting a cosine theta. Right? So that's why this is in a spherical system, and our observation. So this is observation point. This is true only when observation point on z-axis. If it is not on the z-axis, we have to change this, and that will be called spherical harmonics. Like this will generalize it, so there will be more components. For each piece, you will get more components. So that's called the spherical harmonics. Did I answer your question properly?
Yeah.
Ask again.
Well, I was asking if the R prime is a vector, which that answered kind of a different question, but even in the dipole and the quadrupole, because those are still vector quantities.
This will be, so this is if you want the magnitude of this. So since it is on the axis, this is only one component. Like if it is, you can say this is the R hat component. I think that's what this is. R hat. So remember that R hat theta, right? R hat phi. So this is in spherical coordinates. Yeah. Hopefully I'll address this more as we go spherical harmonics. Okay. But it's neat how all this gets organized, so it's kind of nice. And I'll stop here. Thank you. Any questions, gentlemen?
No, I'm good. Thanks.
Good. Thanks, Matt.